Welcome to the wind energy lecture. Wind energy is created when the sun unevenly heats the Earth's surface. Thus, wind is actually a form of solar energy. Basically, as the fast wind comes, it moves the windmill. And again, those that pass through it actually slows down a little bit, which is why we do space them out before regaining speed. The wind is based on differences in solar heating of the Earth's surface. So again, the movement of air. And so the solar radiation at the equator is greater than at the poles. So the tropics are warmer. And so this interacts with the rotation of the Earth, which is the Coriolis effect. So basically the trade winds happen here between 0 and 30 degrees latitude. And then we have the westerlies that are here between 30 and 60. And then we have the jet streams that come around. So all of these effects are going to affect the wind in a localized area. If we look more locally, we can see that sea breezes, for example, are due to differences in the specific heat of water, which is higher than the specific heat of land. So water is relatively stable, but the land temperature fluctuates. Thus, the warm air comes from the ocean. We have the warm air coming up and the cool air coming down, and you see the wind patterns growing. And mountains, again, the cool air warms up in the morning, rises with the cool air moving upslope to replace it. And then during the night, this upslope air sinks into the valley. So we have large scale wind events, and we also have localized wind events. We've been harnessing the wind capacity for a very long time. So if we look at kind of the golden era of windmills in Western Europe, was anywhere from the 1200 to 1850s, where we had 50,000 different windmills, about 18,000 in Germany alone. In 1892, Thomas Edison had the first electric generating stations in New York and London. And this is where we transitioned from windmills just for pumping to actually windmills for electricity production. And so from the 1850s to the 1930s is when you saw a lot of these turbines actually come into the US. And we had as many as 6 million units installed, mainly in the rural areas. Then in the 1930s on, as we actually started to electrify our rural areas, you saw this grid electricity actually displacing some of these multi-blade turbines that had been used in the past. So again, historically, and we still use windmills in the rural areas for water pumping. So again, we also use it to grind mill, to pump water from one place to another. You can use these windmills. So for example, here a water pumper basically has our cylinder here that's being drilled, or it's being driven by the windmill that drives that cylinder back and forth, which then pumps the water up so the animals or people can use that water. So again, once we get electricity though, some of that, those pumps then are replaced by just having an electric pump from a wind pump. If we look at the growth in wind energy, you can see from the 1980s, and this is worldwide, to the end of 2018, where we're over almost 600,000 megawatts of installed electric power from windmills alone. And again, most of this has been growth in land windmills. So if we look here, onshore is again the green, and we can see that the onshore from 2000 to 2019 has grown at a much faster rate than the offshore. And it wasn't until kind of 2010 that we started to see this rise over the last 10 years in offshore wind. And if we look at the different regions, again, most of the installed capacity from 2009 to the end of 2017 has been in Asia in terms of total megawatts, followed by Europe and then North America. If we look specifically here in the US, again, we saw large growths in the past 10 years. If we can see from 2010, we were at only around 45 cumulative megawatt capacity versus now we're at over 100,000. And if we look at where this capacity is located, again, by the end of by 2020, we're again at 100,000 megawatts. Most of it is in Texas. So again, this is where we have the most installed capacity of windmills. Again, followed by Oklahoma and California. And again, our kind of where the wind blows, Iowa, where the wind blows really strong through our plain area. Again, 1,800 megawatts of new capacity was installed just in the first quarter of 2020, which was a 117 increase over that same quarter in 2019. So our capacity is increasing each year. If we look at our total potential wind capacity, it's over, again, we're over like 10 million megawatts. And so this is, again, potential that's technically possible in a given area. We wouldn't expect us to fully utilize this. But again, most of that capacity is, again, where we have our windmills, again, in these Great Plain areas, and to a lesser part in the Appalachians. Again, some of these capacities are quite large. This is a wind farm, 781 megawatts in one wind farm in Texas. And again, this has 625 turbines and can power more than almost 250,000 US homes. And if we look at our resources, again, with the reds and purples being the good resources, you can see, again, as we said, we have all of this resources here, but we also have all of this offshore resources. And you can see here that our offshore capacity is actually much higher than our onshore capacity in terms of the wind speed class. So again, our power classes, a 3 is fairly fair wind speed class, with a 7 being superb. And again, our wind speed capacity, our classes, is much higher offshore. It blows stronger on offshore capacity than inshore. But again, it's more difficult to install our offshore capacity, which is why that has grown at a slower pace compared to our onshore capacity. So again, talking about those wind classes, so we can look and see that if we look at kind of class, let's say 4, which is good. So again, at 10 meters, this would be about 6 meters per second, or about 13 miles per hour. But at 50 meters, where again, we're gonna have our windmills, this is gonna be closer to 17 miles per hour. If we look here in Maryland specifically, we can see that if we look at our onshore capacity, most of this onshore capacity is out here in Garrett County. And so that's where our windmills are concentrated, is in the western part of Maryland. We don't have a lot of windmill capacity currently, but the windmills that we do have are concentrated in this western area where we have much higher wind speeds. In terms of our offshore capacity, again, most of this capacity is out here. And again, if we're looking at outside of Ocean City and our offshore capacity, that's where we have the strongest capacity, but we also have some capacity here in the Chesapeake Bay area. So back in 2008, the US Department of Energy said that we can have 20% of our electricity needs by 2020. Again, right now we're about 11% of our electricity needs for all of our renewable sources. And so they're saying that we could have by 2030, we could have, if we were on the right trajectory, we're not there right now, to have 20% of just wind taking up 20% of our capacity. And this would reduce in, reductions in CO2 emissions, reductions in natural gas use for making electricity, less water use, because again, with coal-fired power plants, we use steam and water, and again, revenue and local revenue as well as jobs. The advantages of wind power is, again, it's inexhaustible. The wind does, we use it and it picks back up afterwards. It's dispersed. So we have it, this isn't like geothermal where we talked about the capacity being for electricity from geothermal being in very specific regions. This is pretty much throughout the US. It's better in other parts. But basically, once you have it built, we aren't emitting greenhouse gas emissions during it. Now, we do emit greenhouse gases during manufacturing, construction, and transport of the windmills. But then once they are in place and built, then it is it doesn't emit greenhouse gases during its operation. So again, that's displacing CO2 sulfur dioxide and nitrous oxides that would be produced from natural gas and coal electricity production. Again, we don't need any water. It doesn't release toxic compounds during the electricity production process. Again, we might release some during the producing the turbines, but not once they're built. Again, a lot of this can be done in rural areas. And again, most of it, we have some maintenance costs that we'll talk about, but most of it's going to be upfront costs. So once we build it, we can continue to take advantage of it for many years. And the disadvantages, which we'll talk about more about, is birds, noise, bats, aesthetics. It's often in rural areas, so we may not have the electric capacity, and so we might have some transmission constraints getting it from where it is to the larger cities. It has a lengthy policy and permitting procedure right now, so it often takes anywhere from 3 to 5 years from saying, okay, I want to build a wind turbine to actually being able to generate electricity. Again, it is an intermittent source of power, and it does have a high capital cost, which is needed up front. If we look at an actual wind turbine, again, we have our blades, we have our gearbox, and that gearbox is going to turn our induction generator, and then we have our computer system. So more specifically here, this is the Nacelle. This is the base of the wind turbine that you've seen. And so we have the top of it. This connects to our blade through a hub. Here's our gearbox. Here's our generator. And then we have a weather station, and we'll go through why we have that. And then that is connected to the tower, which then we have our base, which here is our electricity, goes to a transformer station, and then it goes through to our homes. So if we look again way more specifically, again, that weather station is we do have a hub controller, and we do actually have a lock system. So if the wind does get too high, we actually have these meteorologic gauges. And if it gets too high, we are going to have a brake, and we're going to stop and lock that system. So we do have a parking brake in here. And then again, we have our ball bearings, which might need to be changed. And again, sensors and our gears, which are turning. So when we're looking at building a wind turbine, so first we need to make a base for the tower. So we bring in our heavy equipment to make that base. We're going to dig a big hole. We are then going to put steel reinforcements into that base to create kind of a steel hinge to put it on. We're going to reinforce it. We're going to pour our cement. Here's our tower. So our tower is going to be connected in segments. And so we're going to put a big crane, and that big crane is going to position our towers from our base here. So we're going to position our towers in. So here's our tower base, and then we're going to connect the segments. Here's again, this is the gearbox. So this actually has the gears. This is our Nacelle, the gears, the induction generator, the control systems is all here. And so that's going to be then lifted onto the top. And then we have our blades that are going to be very long. And so then those blades are going to be connected. And then that is going to be attached to the top here in our system. And you can see the meteorological system here. And then finally we're done. And that's our wind turbine. So our costs, this was a study out of Denmark and Ireland, and basically the turbines, the cost of everything we just did there was about 65% of their total cost. Connecting to the grid and upgrading the transmission system was about 12% of their cost. The on-site electrical needs were about 8%, the civil engineering 8%, development 4%, legal financial 3%. So a lot of the cost is the constructing those turbines themselves. Operation and maintenance, again, repairs were about 20%. We had insurance, service agreements, land rental, administrative costs. And that gearbox, just the gearbox box, not the whole Nacelle, but the gearbox can be replaced up to 4 times in a lifetime. But again, the lifetime is 40, over 40, 50 years. And that can cost about 20% just to kind of replace that one part. So again, we've seen the power in the wind equation. So again, our power equals 1/2 the air density times the area of the blade times the wind velocity cubed, okay? With the air density being at standard temperature. So air density is lower at lower temperatures. And so again, our power, if we had a standard air density, 0.6125 times the area of the blades times our velocity cubed. And so because wind increases with the cube of the wind speed, a 10% increase in wind speed translates into 30% more electricity. So 2 times the wind speed is 8 times the electricity. So wind at 10 miles per hour has 3 times as much energy as wind at 7 miles per hour. And then at 20 miles per hour, it's about 23 times more energy than 7 miles per hour. Again, wind increases with the height to about the 1/7 power. As we go up in the atmosphere, we're going to get higher wind speeds. So if we have double the height, it's about 10% more electricity. So again, we have to kind of say we'd rather put it where the wind's going to be really strong because we're going to get more bang for the buck with the strong wind area. And then we are going to go higher, but we don't want to go too high because again, double the tower height is about 10% more electricity. If we look at the air density, the wind speed proportional with air density. So humid climates have greater air density than dry climates, and then lower elevations have greater air density than higher elevations. So the wind speed at Denver at a higher elevation is going to be about 6% less than that at sea level. So that's just a proportional difference. And then the area, again, it's proportional with the swept area of the blades. So we can think about a 10% in the sweep diameter is about, the diameter translates into about 21% more swept area. So again, blades, if it's about 413 feet in diameter, then again, it's going to be about a 600-foot tall total height. So there is a limit. We have the Betz limit, and that's the maximum power that can be extracted from the wind. So basically, Albert Betz in 1919 figured out that the theoretical maximal kinetic energy that we can extract is about 16/27, which is 59.3%, based on the conservation of mass and momentum from an airstream. Okay, so when the wind energy comes in, what's on the other side is a 40.7 and only 59.3 can actually be extracted. And so again, if wind turbines can capture anywhere from 70% to 80% of the energy, they're really capturing 70, 80% of that. So even though it's really efficient, it's of that Betz limit. So 70% of the 59% of the wind actual input in can be extracted into electricity. So there's 2 main types of turbines. We have the vertical axis turbine and we have the horizontal axis turbine. Again, the horizontal axis is the most common, with the blades rotating on an axis parallel to, blades rotate perpendicular to the ground. The horizontal axis is much less common, and they're going to rotate parallel to the ground. It's going to go this way. But again, there's not as many available there. And so again, you can see here we have our gearbox and our generator up high in the sky with our rotator here. Here, all of that's actually going to be here on the ground and with it going here. So these are more often done in kind of on top of buildings or in more urban areas where you can do it more closer to the ground. And these are going to be much taller, and they're going to be done in more rural areas. So again, when we look at our wind speed, there's 3 things that we're going to be looking at. We're going to look at the power curve of whatever blades the power curve of the generator that we have. So we can look here at the wind speed and what the power is. Just like when we talked about PV panels, how much power we're going to get from the different panels. Here's the same thing with the generator that we're using. And then we're also going to look at the wind speed. And as you can see here, here we have the wind speed, and here we have how much energy. And then you have the wind speed frequency. So even though 10 miles per hour is the most frequent, 9, 10, 11, 12 is the most frequent in this place, we're going to get most of the energy from that 18 and 20 miles per hour. So these are not, 18 is not the most frequent, but because it's cubed for the velocity, that's where most of our power output is going to come from. So again, we really want class 4 for utility scale winds. Again, we want to think about what is the distance and what kind of voltage capacity do we have to put onto the grid. We need to think about permitting, public acceptance. Again, even in, we'll talk about this, but even in like Maryland, there's been a lot of resistance to siting wind farms. There was a big group out of Kent County that was against siting wind farms there. So there's definitely public pressure in terms of where we put the wind farms and how acceptable they are for the community. Sometimes it's because there's noise involved, there's visual, and birds impacts are usually the biggest concerns. Also the land area. Again, if you're just going to put the infrastructure in to put one tower in place, it might be cheaper to have economy of scale and put many towers in a certain area, because you're bringing in all the infrastructure to build those bases and to do the construction projects. So if we have a large land area, we may have to deal with a number of owners. Again, we're also going to look at the roughness of what's around us. So again, if we have water or ice, again, if it's an offshore one, we're really not going to disrupt the wind that much. Versus if we have low grass, same thing. If we have something that has like woodlands, there's going to be a lot of disturbance of, you can see here, disturbance of the wind that's going through our windmill. So even though our windmill's way up here, we want to minimize the disturbance below, because that's going to kind of change the wind pattern, and it may not come in exactly perpendicular how we want it to the windmill. So when we look at, so wind maps are going to give us an idea of the potential resources. So what we're going to do is we're going to put in a weather station, and basically for 9 to 12 months, we're going to map out. So this is just a little tower that we're going to put in before we bring in this big base, to make sure that we're putting it in the right place. Because again, calculating that frequency of wind speed and how often we get that 18, 20 miles per hour is really important for our energy output. So if we look at having the same average speed, doesn't necessarily mean the same capacity. So if we look at these three places in Puerto Rico, New York, and California, they all have a mean speed of 14.1, but they have very different power outputs. And so here's kind of an example. So for example, you get 8 miles per hour for 1 hour, and then it's 3, and then up to 10. And so you have 7 miles per hour being the average here. But here we have 5, 8, and 8. So also the average is 7 miles per hour. But when we look at, again, that one that had the 10 miles per hour versus the 7 miles per hour, that output from the 10 is much higher. So even though it just had 10 for 1 and then it was down for 3 for 1, what ends up happening is that 8 miles per hour gives us some. The 3 didn't even give us any. It was below our wind curve here. It was below, it was not enough to even move the turbine. But that 10 gave us so much more that we actually got more power from this windmill that had the same average speed than another windmill that was a more consistent 5, 8, and 8. So again, you need to be looking at your cut-in speed, again, when it cuts in, when it's going to start actually rotating. And then here is going to be your rated power. So this is what they're rating for. So, you know, you're kind of 10 to, it needs to get up to about 10 or 12 miles per hour. And then here's where we're going to do our really great power. And then at some point we're going to cut it off though, if it gets too high, just to protect our thing. So we'll see this rated power curve. And so this is for each turbine. Where are we going to be able to produce our maximum electricity based on the wind speed? So then the actual electricity we're going to get though is going to be again based on our wind speed frequency. So here's our frequency and our annual energy production based on our wind speeds. All right. Thank you very much for listening, and I hope you have a great weekend.